Hello everyone. Today we will continue discussing together the topics of the three-phase induction machine. In the last sessions, we discussed the operation, the idea of the operation of the induction machine, and we derived together the equivalent circuits of the induction machine. And we discussed also the power flow, how the power flow in the induction machine as a motor. And we mentioned that induction machine is going to be used in industry mostly as a motor. It doesn't mean that there is no induction generator, but the majority of the applications for the induction machine in the market is in motoring mode. Induction generator can be found, as we mentioned before, in some applications like wind energy applications, and in some precise applications like two-phase induction motor, for instance, not three-phase, different than the three-phase induction motor. Sorry, three-phase induction motor, yeah. So we can find two-phase induction motor in some control. It's called two-phase induction machine or AC servo motor. You can find also single-phase induction machine as a motor at homes, but generator-wise, this is going to be in wind energy application. Three-phase induction motor is the most well-known induction machine used in industry. We can say like maybe more than 70% of the motors in industry are induction motors. So for that, we are going to continue focusing on the three-phase motors. Our objectives of this material, we need to drive the induction motor torque speed characteristic. So in order to make any kind of analysis, we need to have characteristic, like what we had before for DC motor, for instance. So what is the characteristic? The characteristic for any machine is going to be the output characteristic. So since this is a motor, so we expect mechanical output characteristic. So the mechanical output characteristic for any motor is going to be the torque speed characteristic. So how is omega with torque? So you remember that DC motor was like that. So this is for DC machine, for instance, the shunt or the separately excited. Induction motor, we will drive the characteristic together. We may end up with something close to the DC motor, something like that, but it's a bit different in shape, okay? And you know that, so this is for induction, and this is what we will drive today. And you know that for synchronous machine is a constant speed, whatever the torque value. So we can say this is here constant value, and this is synchronous machine. So these are the three different types of machines we are using in industry: AC machine or DC machine. Okay, the most well-known machines used in industry. So this is the first objective we need to do in this material, driving the torque speed characteristic. And in order to do that, we have to have a mathematical model for the machine itself. So we'll drive the mathematical model of the induction motor. In addition to that, we need to learn the performance of the induction motor. The performance means how the motor will interact when we increase the load, what will happen? When we decrease the load, what will happen? So this is the performance that we need to investigate. Besides, we need to drive the maximum torque of the induction motor. So what is the maximum possible torque that we can apply for an induction motor? We will call it T maximum. And learn the different modes of operation of the induction motor. One of the modes is going to be generating mode. The modes of operation of induction machine, not motor. Okay, so one of the modes is motoring mode. Another mode is in generating mode, and we have a third mode. So we will see what other modes of operation we can see for the induction machine. So this is going to be the topic of these materials. We may need to have 2 sessions to finalize these topics here. So let's start together with the motor equivalent circuit. I know that in previous sessions, guys, we discussed different types of equivalent circuits. So we discussed the exact equivalent circuit. However, for simplicity, we can go with an approximated equivalent circuit. So what is the difference between these circuits? Let me give you a quick. So firstly, for this equivalent circuit here, guys, you remember that the exact equivalent circuit, the resistance R1 and X1 were here in this place, okay? But we mentioned that because the value of the impedance referred to stator side is very small, we can neglect the voltage drop. And if you neglect the voltage drop between the input volt and the magnetization branch across this impedance, so we can move this impedance to that side. So this is a first approximation. What this approximation is going to do, in order to figure this out, let me draw another circuit right here. For instance, guys, this was the exact equivalent circuit that we have for the single line diagram of the induction motor. Here's the supply volt. This is R1. This is JX1. This is R core. This is JXM. This is JX2 prime. This is R2 prime. And this is R2 prime times 1 minus S divide S. So this is the mechanical output resistance. So this is the exact equivalent circuit. In the circuit you see, guys, now, if you would like to make a circuit analysis in order to find or drive the performance of the machine, and for any machine, you need to drive the performance, so you need to make some circuit analysis. In order to do circuit analysis here, you can make nodal analysis at this point, and you have the volt here, so this is the supply volt, you know that one. And the target all of the time, guys, is to get this current right here. So I'm going to say this is I2 prime, this is I1. So this nodal analysis, guys, is going to be relatively complex. So we can consider this is the ground of our circuit. So in order to make such analysis, this is going to be relatively complex, okay? If you prefer to make loop analysis, so you will have one loop here. This is a second loop. This is a third loop. But if we make this approximation, moving this branch to that side, so the circuit is going to be like that. So here we have our magnetization branch. Here we have the reactance on the other side, and then our resistances. And I'm going to say this is resistance 1, and this is another resistance here. Let's collect all of them together. So this is going to be JX equivalent, and X equivalent is X1 plus X2 prime. This is R equivalent, which is R1 plus R2 prime, and this is a variable resistance R2 prime times 1 minus S divide S. Or if you would like to reshape that, so the total resistance can be R1 and R2 divide S. So this would be the total resistance here in this circuit. If you would like to make now analysis in order to get the current here, you don't need to make very complex analysis because the volt here is V1, so you can say definitely here I2 equals V1 divide this impedance here, which is R1 plus R2 prime divide S plus JX equivalent. That's it. So we got the value of I2 prime, and we can make any circuit analysis you need or investigate the performance. So you don't need to pay attention to make very complex circuit analysis. For that, this is a very nice circuit approximation we can do. So let's go back again here to this circuit. So this is the first approximation that we can do in order to simplify the circuit. If we refer the magnetization branch terminal and neglecting the core branch in calculation, and neglecting just in calculations here, guys, because the core loss is going to be constant or given. So in this case, the circuit would be as simple as you can see here. So you have the JXM, you have the total resistances R1 and R2 prime divide S, and the total reactances. And this is here again the I2 prime. For sure, the air gap power is still the power across the rotor side, okay? So power flow is going to be the same. Can we do more approximations? Actually, yes, but we're not going to make more approximation than this one. We are going to consider this one, but in some books, you can find that this branch even is removed, okay? But I don't recommend to have very simple or very like approximated circuit like that. So include the JXM in your analysis. This is much better. Another equivalent circuit, guys, this equivalent circuit is used in books. It's called IEEE equivalent circuit or IEEE recommended equivalent circuit. So you know IEEE institution is the Institution of Electrical and Electronical Engineering Society. So this society actually makes standard and makes a lot of things to electrical and electronics engineers. So one of the things that they recommend is the equivalent circuit of the induction motor. So they recommend that equivalent circuit, and they have very nice way to solve the problems of the induction motor using Thevenin analysis. Okay, so they did not make the approximation of moving the stator impedance to the rotor side, but they just neglect the core resistance in the circuit. Okay, so this is one of the circuits also used in the book. However, in our course, guys, we are going to focus on using this circuit. It's going to be very simple in computation and accurate enough to investigate the performance of the induction motor. So let's start now with our circuit, and we need to drive the torque speed characteristic. As we just write down here the relation, how can we get the current from this approximated equivalent circuit? So this is very simple current equation. So as you can see here, guys, this is our circuit, and in order to get the value of I2 prime, so we just divide V1 over this impedance here. So I2 prime is V1 divide R1 plus R2 prime divide S plus JX equivalent, where X equivalent is nothing but the stator leakage reactance and the rotor leakage reactance refer to stator side. So this is the equation of the current. As you can see here, guys, this is complex number, which gives you now the magnitude and angle of this current. If you would like to get just the magnitude, so it's easy to square this current to cancel the roots in the equation. So let's squaring this equation is going to be now V square divide real part square plus imaginary part square of the denominator. So we can say it's V1 square divide R1 plus R2 prime divide S square, which is the real part of the denominator, plus x equivalent square, which is the imaginary part of this denominator. Take care, guys. V1 is phase volt because this equivalent circuit is single line diagram. So this represents a single phase, and the other two phases are similar to that one. So if you consider the machine is Y-connected machine, so V1 is going to be, in this case, a phase volt, which is V line divided √3. So in case of Y connection, this V1 equals V line divided √3. Okay, after getting the value of I, 2 prime, and we got I square, I can make any analysis I need here. So let's firstly get the torque by means of the gap power. You know that gap power is going to be the power across this resistance. Because, as you remember, we discussed that in the previous sessions, this is the stator impedance. So once the current flow out of the stator, it's going to go to the rotor side, and the only resistance remaining in the circuit for the rotor side is R2 prime divided S. So this resistance will represent the resistance of the transferred power from stator side to rotor side, which is the P air gap. So P air gap can be represented by this resistance times I square times 3, because this is three-phase machine. So we can say that the torque, the developed torque of the induction motor equals P air gap divided synchronous speed. Why synchronous speed? Because this is the speed of the flux in the air gap. It's not the rotor speed. So the developed torque depends on the magnetic field coming from stator to rotor, which is rotating with the synchronous speed all of the time. So again, P air gap is nothing but 3 I square times R and divide S. And you know, here we have omega S, so this is going to be our equation now. If you replace I square by the equation we have right here, you will end up with this equation. So torque equals 3 V1 square, and V1 has to be phase value as we discussed, times R2 prime divide the denominator, what we have here. So this is the denominator of the current times S omega S. By the way, if the machine is Y connected, as we mentioned, and you know that V is going to be V phase. So when you make this calculation here, if you replace V phase by V line divide √3 square, so replace V1 square by V line divide √3 square, and you have 3 here, so this 3 will be omitted with the √3 square, so it will end up with, instead of 3 V phase square, it's going to be V line square. So you can use it also. V line square divide times R2 prime divide this denominator. Okay, so this is mathematically how can we do that calculation. Now, I'd like to draw the output characteristic of the induction machine. When we discuss the DC motor, guys, we discuss the relation between torque and omega. Here, we can do the same, but standard-wise, we drive the relation between torque and slip. Why? Because actually, the motor speed omega, omega rotor, equals 1 minus S times synchronous speed. If it is in radian per second, if it is in RPM, so we can say NR equals 1 minus S times ns, synchronous speed in RPM. ns is constant value, and S is going to be the variable all of the time. So we can say it's torque speed characteristic or torque slip characteristic. Both are fine. So omega S in the equation here is going to be constant. So omega S is 4 pi F divide number of poles. Okay. Because it's nothing but 2 divide P times omega electrical, and omega electrical equals 2 pi F, as you know. So this is the equation of the omega S. Okay, if you would like to get it from the synchronous speed, so it's going to be from the RPM relation, it's going to be the same also. You know that in order to convert from RPM to radian per second, so you need to multiply times factor. So ns is 120 times frequency divide number of poles. So you need to multiply that times 2 pi divide 60 in order to convert from RPM to radian per second. So this will end up with the same value you have here, which is 4 pi F divide number of poles. So this is the omega S. So omega S is constant. V is constant as well. The resistance is constant. R1 is also constant. X is constant. So you will find by the end you have only the S is variable. So we need to draw this curve. How can we do that? So if you have some values for your motor parameters, and you can have it from any mathematical or from any data sheet or from any motor manual. So you can get the parameters of the motor and then use these parameters to draw the curve. We will show you guys how to do that in MATLAB simulation, how to drive or draw the characteristic of the machine using MATLAB simulation, MATLAB Simulink. So just change the value of S for the range of a change, and we will discuss the range of change now, and observe the corresponding torque. So what is the value of S? You know that S equals ns minus nr divide ns. So for any motor would start running from scratch, the speed of the rotor in the beginning is going to be 0 and increasing until being very close to the value of ns. So in this case, guys, we can say that the value of S is vary between 0 to 1. Because if nr equals 0, so S equals 1. So S equals 1 as the motor starts. And once the motor runs, this speed is going to increase until reaching to nr, which is very close to ns. So in this case, if you assume that nr reached to ns, it's going to be 0. So theoretically, it's 0, but we're not going to reach to the 0 value because the speed has to be less than the synchronous speed. For that, guys, if you draw that curve on MATLAB, you will find this graph. So let me clean around this graph here. So this is, guys, the graph that we can get. Here is S or speed, and here is torque, T. I know it is like flipped compared to the torque speed characteristic we have for the DC machine, okay? But you can find the standard curve also in some other books. So you can find the slip or speed on the vertical axis, and the torque is on the horizontal axis. Okay. So as you can see, guys, here, S here, or the speed of the motor here, is going to be at starting. So S here equals 1. And the machine starts at this point. The torque is increased until reaching to a certain value here, which is going to be the maximum value of the torque. So this is T maximum. And then it will decrease, the torque will decrease until the speed reaches to the synchronous speed. So this is the point of synchronous speed here, and at this point S equals 0. For this characteristic, guys, as you can see here, it's mentioned here that this region is unstable. So all of the region from S equals 1 to S at maximum torque, which is going to be called S maximum. It doesn't mean the maximum value of S, but S maximum refers to the slip at maximum torque. Okay, so this is S maximum. So all of this region, guys, is referred to as unstable region. Unstable means if you operate the motor here in this region, the operation is going to be unstable. You should learn that in control what the meaning of stability and make stability analysis in control classes, okay? But I'm going to give you a quick physical representation for the balanced or stable or unstable system. So if you have a cup like that, and you have a small ball inside like that, and you applied any disturbance to that ball. Disturbance means like moving this ball by your hands. What will happen because of the shape of this cup? The ball is gonna move around and it will return back again to the same point. Which means when we had a disturbance on this ball, the ball has been oscillated a bit, but by the end, it returns back to the same operating point. This is the meaning of stability. So if the machine is working in a region on the characteristic and you applied a disturbance on that machine and the machine started oscillating and returned back to the same operating point again, this is called a stable region. So the opposite is going to be the unstable. Assume that you have a cup like that and you have a ball here on the top. When you apply any disturbance to that ball, just move it with your finger. So it's going to move this direction or that direction and will not return back again. Which means the disturbance changes the operating point. And this is the meaning of the instability for any for any system or for any motor. Actually, this what will happen for the motor in this dashed region here. For that, we call this region is unstable region. This doesn't mean, guys, we cannot operate the machine in this region. However, if you would like to operate the machine in any unstable region, you have to use closed loop controls. And the function of the closed loop control, you will learn that in control classes. The function of the closed loop control is to add some compensators to the system in order to convert the system to a stable system. So the system itself is unstable in this region. Okay, so the induction motor model, you will learn and control that for any motor, for any system, you will have transfer function. And from the transfer function, you can get zeros and bools and everything, and you can draw the S-plane of the plant, okay, and investigate if it is on the left-hand side or right-hand side, and based on that, you can decide if the system is stable or not. What the controller is doing, what the closed loop controller is doing, the closed loop controller adds some multipliers to that transfer function in order to make your system stable system, okay? So this is the idea how to operate the machine even in unstable region. You have to have another compensator or closed loop control. We're not going to go more in deep in the control classes, so you will learn that in control classes. But for the time being, you need to know that the region here is unstable. It cannot be used with open loop control. Open loop control, guys, means you have a motor, just supply the motor and operate it. This is open loop. Or just you would like to have controlling the speed by changing the volt, so you have just a variable volt or variable supply and change the supply manually or even automatically, but without a feedback. But closed loop control means you have to sense the output speed, compare this output speed with a command speed you have, take the error and apply this error to a control system, and this control system works to minimize this error to zero. So this is the concept of the closed loop control, okay? So if you are not going to use closed loop control, you have to use the motor in this region. So the operating region of the motor now, the stable region, is going to be from here, this point, to that point. This is the theoretical region that we operate the motor. But let's go more in deep and understand, guys. Now, can we operate a machine at maximum torque? Actually, maximum, guys, means the point that if you try to go beyond this point, the machine will be broken. So you cannot have a torque higher than the maximum torque on your motor. So this point is very critical. So we don't go toward this point. It has to be less than this point. So we can say that we are not going to move after this point, for instance. And from the other side of the curve, theoretically, S here equals 0. We cannot reach to this point as well because the machine speed has to be less than synchronous speed. So we will not reach to that point. So we can say this is a range that we operate our machine right now. So theoretically, it's from S equals 0 to T maximum, but it's going to be a bit less than this part. Here, this curve, guys, is drawn like a bit wide to allow you to understand the concept. But this part, guys, is going to be a bit stiff. It's not going to be with very high range like that, which means if here S here equals 0, from the figure here, I can say if this is S equals 1, this is S equals 0, I can say this is around 0.25, for instance. However, you can find that S maximum is like 0.1, which means this part of the curve can be very stiff like that. Okay, nice. So we will see that in some problems or some analysis on MATLAB. Okay, so understanding the curve is very important. Understanding the boundaries of the curve is very important. So we mentioned that, again, the different boundaries we have here. At this point, S equals 0, which means NR equals NS. This point represents the maximum torque, and the slip at this maximum torque equals S maximum. And this doesn't mean the maximum value of slip, but this is the slip at maximum torque. And this point here is the starting torque, and starting torque will be at value S equals 1. So these are the curve boundaries that we need to understand for the three-phase induction motor. Now, start again from our equation to drive more important relations for the induction machine. So this is our torque equation again, guys. In order to get the maximum torque, mathematically, to get the maximum or peak value of any curve, you can get it by making d by dt or the variable, okay, and make this derivative equal 0. So our curve here is a relation between torque and slip. So I can say that the maximum value of the curve here, T maximum, can be obtained if S has been changed, and at the point of change, if d by ds, if dt by ds equals 0, this means we are on the top of our curve. So this is our equation here, guys. If we make dt divide ds equals 0, we can get the condition or the value of S that will produce the maximum torque. So I'm going to say dt maximum by ds equals 0, and the corresponding value we will get is going to be called S maximum, which is slip at maximum torque. So this is going to be that S here, S maximum. How to make derivative for this equation? If you have a fraction like that, numerator and denominator, so the d by ds here is going to be the denominator times the derivative of the numerator minus numerator times the derivative of the denominator divide the denominator square. So from here, guys, you can end up with the value of S maximum. We are not going to drive that right here in the class. Okay, you can find that in books. But the relation that you can get if you make this derivative is going to be Sm, which is maximum, S maximum or S at maximum torque, equals square root of R2 prime square divide R1 square plus X equivalent square. So if you take this value now of S maximum and substitute in the relation of torque, so replace S by S maximum, you will get the equation of T maximum. And this is going to be the equation of T maximum. So T maximum is 3V1 square divide 2 omega S times R1 plus R1 square plus X equivalent square. So this is the maximum torque. Now, guys, I'd like you to compare this maximum torque with the equation of the torque here. Do we have R2 in this curve, in this equation? We don't have R2 prime in this equation. We have R2 prime here in the upper equation. This means if the value of R2 prime is changed, the maximum torque is not going to be affected. Someone can say how the parameter R2 prime can be changed. R2 prime is nothing but the rotor resistance. This is correct. So you can add external resistance to rotor in the slip ring induction motor type. And actually, we do that for the purpose of speed controls. So this means whatever the value of R2 prime, the maximum torque is going to be constant. And this is one important thing you need to figure out. So this is the maximum torque equation. Again, 3V square, and again, V is V phase, 2 omega S times R1 plus square root R1 square plus X equivalent square. If you compare between the two torques, what does it mean? I may have an operating point here, And I'd like to compare this operating point with the maximum torque. So I'm going to say this is T and this is T max. This is operating point number 1, and this is operating point number 2. So I would like to get a relation between these two operating points in order to make some calculations. So simply I can say T divide T maximum. So I will divide this equation T, divide T maximum, and all values of the equation here are going to be for the first operating point. So V at the first operating point, R2 prime, R1, all the equation as the first operating point, and S at the first operating point, which is S1 here. And the other operating point is the maximum torque. So all the parameters will be referred to the maximum torque. So if you do that, guys, divide T over T max, you will find this relation. It's a relatively complex relation, but I'm going to simplify that with you right now. So T divide 2T maximum plus A times S maximum. What is A? A is R1 divide R2 prime. So we'll define a factor here called A. A is R1 divide R2 prime. So 1 plus A times SM divide SM divide S plus S divide SM plus 2A times SM. Why we get the function as a function? Why we get this relation as a function of A? Because most of the time we will neglect R1 in our calculations. R1 is the stator resistance, and for high power, guys, we agree that the stator resistance is going to be very small, and we did that also for synchronous machine, if you remember. So for high power machine, and this is a target in our course, we are discussing deeply for high power machines. So R1 is going to be neglected. If R1 is neglected, guys, so the value of A is going to be 0. So if you apply here A equals 0, this term will be removed, and this term will be removed also. So it's going to be 1 divide S maximum divide S plus S divide S maximum. So if we do that, our relation is going to be more simple. One more thing, guys. If I would like to compare two other values, two other operating points. So I have a certain curve like that, and this is the machine characteristic, and I have two operating points. Operating point number 1, operating point number 2, and none of them is maximum torque. So you know that the torque is, or the torque relation is basically coming from the power. So torque is proportional to I square R 2 prime divide S. The power is 3I2 prime square R2 prime divide S, and the omega S is constant. So if you compare two, let's say here omega S also because it's proportional to. If you compare two torques together and the machine is working at the same frequency, which means the same speed, so you can say that we don't add resistance. So we can say for that speed control or for that two operating points, the torque is proportional to I squared divide S. So T1 divide T2 equals I1 squared times S2 divide I2 squared times S1. Why I'm discussing these relations, guys? Because these relations are used a lot in our numerical examples to compare between the operating points to solve or do the performance analysis of our machine. If you apply A equals 0 by neglecting R1, so again, if R1 equals 0, so we neglect R1 here. So the relation of S maximum ends up with R2 prime square divide X equivalent square. So square, square, and we have root here. So it's going to be now R2 divide X equivalent. So this is the maximum, this is slip at maximum torque, R2 prime divided X equivalent, if the resistance R1 is neglected. And if you use that in the maximum torque relation, so you can see here the maximum torque relation we just derived. So this is the maximum torque relation if R1 equals 0. So this is 0, this is 0. So you will end up with 3V square divide 2 omega S X equivalent square. So this is the maximum torque at R1 equals 0. Okay. So when you compare now 2 points, one of them is the maximum torque. So we can use the same relation at A equals 1. So T divide 2T maximum equals S times S maximum divide S maximum square plus S square. This relation also will be used in our questions. So these relations, guys, are very important. You need to write down these relations in your formula sheet when you start solving any question. Now, if you compare 2 points and the maximum torque is the third point in your curve, so can we do that? Yes, we can do that. So we can say I1 squared divide I2 squared equals 1 plus S maximum divide S2 square divide 1 plus S maximum divide S1 square. From where we got this relation, actually, it's from using that relation and that relation as well. So using the two relations as well as together in order to obtain the value of I1 to I2 of the 2 points, and the maximum point is a midpoint. And we will see, guys, how to use all of that in our questions. So let's stop at this point, guys, and we can continue discussing the meaning of starting torque from the next session. Thank you so much.